Okay, so next talk is distributed algorithms for incrementally maintaining multi-agent simple temporal networks, and the talk is given by Jim Boerkoel. Sorry.
All right, good afternoon. My name is Jim Boerkoel. Today I'll be presenting work that I did in collaboration with Leon Plonkin at TU Delft. This is work that I did during a visit to the algorithmics group at TU Delft. So we should mention that this is funded by the NSF Extended Lab Visit Program. So thanks to NSF and Sven Koenig in particular for funding this. All right. To start, I want to give you a brief high-level motivation of some of the work that's going on in the interactive robotics group at MIT, because I think it's a nice motivation for the work that I'll be presenting. So there's been a nice shift in industrial robotics over the last couple of years, and the old model of industrial robotics are these very large structural kinds of robots that are caged off from human beings. And the shift has been towards more collaborative, inherently safe, more mobile, flexible robotics that humans can work in close collaboration to. So there's been recent hardware developments, for example, the ABB robotic arms, which are inherently safe, and also Baxter, the robot put out by Rod Brooks at Rethink Robotics. So not only is it inherently safe, but it's very flexible to program. So the goal here is to develop fast, dynamic, multi-robot scheduling algorithms that are able to be very robust to disturbances, but also adaptable to human coworkers. So humans make relatively unpredictable coworkers relative to other agents. So in particular, we're interested in answering temporal queries such as, is the temporal information consistent? Can we schedule this to begin with? And if so, at what times can different activities and events occur? Or also, what are the possible relationships between different activities in our domain? In particular, we're interested in asking these queries not only in a distributed setting, but also as information gets updated or constraints get added to our network. All right, so brief background. We formulate our basic problem based off of the STP, the simple temporal problem. It's a temporal-based CSP where the variables are time point variables, unlike the finite domain CSP talk that we just heard. The time point variables represent events and have a continuous domain. So these can be things like the start or end time of various activities. So here we have both a drill and a fetch activity, for example. Each of these, as I mentioned, has a continuous domain, and we typically think of these as being defined by bounds. So let's say we're scheduling a shift from 1 to 6. The constraints in this domain are typically temporal difference constraints. They're inherently binary and are expressed as bounds on the difference between two time points. So for example, if we wanted to bind the duration of an activity, we'd do so by saying, for example, that the end time minus the start time is at least 40 and at most 70. And as you can already see off to the side, we've been building what's called a simple temporal network. It's a nice graphical representation of the STP that we can translate and use algorithmically. So algorithmically, it's typically more convenient to represent this as a weighted directed edge, where the lower edges we flip and make a negative there. The advantage of this, and then the other thing that we can do here is we can change domains to just be another edge in the graph. And we do this by creating this, what's called the zero time point. It basically represents the start of time. And so, for example, these edges represent the range from 1 to 6. The advantage of this representation is we can take any off-the-shelf shortest path algorithm and propagate information throughout this network. And this can be used to make inferences and propagate constraints. So the extension to this, recent extension to this is the multi-agent STN, which supports reasoning in a distributed environment. So intuitively, you can think of the multi-agent STN as simply being composed of n individual STP subproblems, one for each of the agents, n agents in the problem. In addition, we also allow for a set of x external constraints, and these really relate the problems of different agents. And what this does is it allows us to limit joint reasoning to only those shared portions of the multi-agent STN, those that are directly involved in external constraints. The flip side is that everything else remains somewhat independent. Conditionally independent is one way to kind of think of it. All right, so as an example problem, we have two robots, two manufacturing robots, A and B, and a human inspector. We have a variety of activities, and like we already saw, we can build up constraints between each one of these different activities. If we had 3 separate problems, we could represent them simply as 3 separate STNs. No problem. What makes these interesting is when we allow for external constraints. So the external constraints in this domain, and this problem, are the dashed lines here. So let's say the human has to perform some sort of routine maintenance on robot B. We can do that by having a synchronization constraint. So the lower bound and upper bound both have to be 0. They have to do this at the same time. But perhaps robot A is currently occupying the space where this needs to occur, and so we need to give robot A time to transition out of that space before these robots can transition to. So these are the other constraints. I'm going to briefly review some of the typical algorithms used for solving and computing information for STNs. So most of you that are familiar with STNs are probably familiar with full path consistency. This is basically applying an all-pair shortest path algorithm, such as Floyd-Warshall. The result is this fully connected network or graph structure. And there are some improvements on this, as recently as ICAPS 11 by Leon, my co-author, that take advantage of sparse structure, but at the end of the day, you're basically calculating this fully connected graph. Well, in many applications, this is wasteful, right? You don't have to really need information about every single pair of edges, especially, for example, in a multi-agent environment where a lot of these edges require communication and are costly. So more recent algorithms, for example, the triangle STP or the P3C algorithm, take advantage of a chordal graph structure. So basically a structure that the largest non-bisected cycle is of size 3. The advantage of this is it's much less information to compute from the get-go, with many of the same advantages of the fully connected, full path consistency version. So one extension of this is the incremental version of partial path consistency. So this is an algorithm from an ICAPS 3 years ago from Leon. And the idea is, let's say you have an update on one of the edges. Really, this edge update is probably not going to propagate to the entire network. So repropagating the entire network from scratch is wasteful. All we really want to do is revisit the edges that were really affected. So that's the incremental PPC algorithm. The other extension, as I already mentioned, is the multi-agent framework, and then the corresponding algorithm for solving that. So this is where the time points belong to different agents, and we can propagate information in a distributed setting. So where Leon and I converged on this particular paper was in the intersection of these two. So we took my multi-agent framework and combined his expertise in incremental algorithms, and we developed 2 new algorithms for solving and maintaining temporal information in a distributed and incremental way. All right, so revisiting the example problem, here we have the original constraints. An example of a partially path-consistent network is this one. You'll see that we've added some edges to form the triangulated structure. And as you remember, there's that z time point implicit on each one of these edges that also forms a triangle. So what we're after is an incremental update. So let's say one of these edges is updated, we get some new information, and what we're after is basically only revisiting those edges that need to be updated. All right, so I'm going to present 2 different algorithms for doing this. Both have a very different trade-offs and are useful in different settings, and we'll get to that in just a moment. So the first is based on the original triangle STP algorithm by Zhu and Shaori, and the idea is that for this particular algorithm is that each agent will maintain a queue of triangles. And anytime an update occurs, you just take that triangle, any triangle that is a part of that edge, or that edge belongs to, and add it to the queue of any agent that shares that edge. And what happens is each agent processes their queue until their queue is empty. And as soon as they compute an edge update that it might be relevant for some other agent, they send a message to that agent. The advantage of this approach is it very quickly propagates information to other agents. The downside of this is that it may lead to redundant computation. So agents are unlikely to sit idle in this approach, but they also might be revisiting triangles many times before they converge on a solution. So let's illustrate how this works. We have 3 queues for each of the agents here. And once again, we've updated this edge on the bottom. So this leads to 2 triangles being added to the queue of agent H in this case. So there's the triangle formed by this triangle. And so that's the second triangle on the queue. And then there's the triangle formed, shared with that 0 time point Z. So what happens is at this point, agent H would propagate that triangle, which then leads to messages being sent to a couple of the other agents, which then add triangles to their queue, and this process continues until all of the information is propagated throughout the network. And agents can process their queues completely concurrently and asynchronously from one another. So that's algorithm one. The other algorithm is a distributed version of the state-of-the-art incremental partial path consistency algorithm of Leon. And what it does is it decomposes that multi-agent STN structure into what's called a click tree. So here's an example of a click tree where corresponding to our example problem. And the new insight here is that we can get by only propagating outward when a tree node is completely done. We take any edge update that occurs within a clique, we propagate entirely throughout that clique, and then we can branch to the neighboring cliques only when we've fully propagated that clique. And by doing it this way, we are guaranteed to avoid any redundant work. So the advantage of this is that we minimize work, but it does introduce some level of synchrony between these different operations. So again, let's illustrate with an example execution. We're updating the exact same edge, which is involved in this maximal clique here. So this is a clique of size 4 involving these 3 time points and also that z time point. So what happens is the H agent would propagate all of this edge information, which then would get propagated to the neighboring clique, in this case, this epsilon clique, which belongs to agent A, which in turn gets propagated and so forth until we fully propagated this network. So you can already see that there's a little bit more synchrony because we have to wait longer until another agent can start executing this concurrently. And concurrency happens anytime there's a branching factor in that clique tree. All right, so to evaluate these algorithms, we developed a simulated distributed multi-agent message passing environment. And this is a simulation that we executed on a single processor. And the code for this is available publicly for download. So you can use this to design your own multi-agent simulation. And we did this in 2 settings. We did it in a no latency setting and then a very high latency setting, trying to emulate basically a very slow internet connection, essentially. We did this across 50 random seeds. We measured both the simulated runtime and also the number of messages. I won't be reporting messages on this talk, but I have slides, so if you have questions, feel free to ask. All right, so we evaluate on 2 sets of problems, and these are both publicly available for download for you guys to test your problems on today and your algorithms on today. The first is an extension of Luke Hunsberger's original single-agent STN generator from his work in the temporal decoupling domain. Basically, we run that generator n times to generate n agent subproblems, and then also generate an extra x constraints to relate the problems of different agents. And we evaluate in 2 settings. We evaluate both as we scale up the number of agents and scale the number of external constraints proportionally to that. And then the other setting is that we scale up the level of coupling. So we hold the number of agents constant and add more and more external constraints. And the way we do this is we take a network with no constraints and we incrementally add each one of these constraints one at a time. So I'm going to highlight a few of our results. The first result is that both of our distributed algorithms achieve significant speed up over the state-of-the-art centralized approach when we have no message latency. This is good. In particular, the DIPPC algorithm, that second algorithm, is at least an order of magnitude above basically any other approach across the domain here. However, when we look at the high latency situation, the DI triangle SDP does better. So one potential reason for this is that it's propagating information as soon as it gets it. So the fact that these messages are getting a bit delayed actually doesn't impact it that much because the computation ends up being not redundant often enough that it is okay. Whereas the more synchronous DIPPC algorithm gets penalized by that high latency a little bit more. So very similar results as we scale up the number of external agent constraints. Basic trends hold right here. So the second set of experimental problems that we evaluate on are based on real multi-agent manufacturing problems. These involve N agents and T tasks, and they simulate basically a multi-robot assembly task on a factory floor. And once again, we evaluate in two settings. The first is as we increase the number of agents. So we increase the number of agents and then grow the number of tasks proportional to that. And then the other is when we hold the number of agents constant and then increase the number of tasks. The difference here is that we're not necessarily changing the constrainedness of the problem. The constraints just come from the natural constraints that would arise from the factory floor. And in this setting, we incrementally refine the network. So we start with a given network and then just add some refinement constraints, what we call refinement constraints. This is basically like a domain expert saying, well, I actually know a little bit about what happens on a Monday versus a general factory day. Once again, this is publicly available for you to evaluate your algorithms. The two main differences, a lot of the same trends hold from before, but two main differences are that first, the DI triangle STP algorithm is now superior no matter what the latency setting is. And this really tells us that DI triangle STP is good at well-structured problems where, for example, there's an entire string of activities. And so the advantages of very carefully traversing the structure of the graph aren't necessarily as high. And then the other difference here is that there's much more evidence of a possible crossover point between the centralized approach and our distributed algorithms, even in the high latency setting. And this is more pronounced as we increase the number of tasks. So you can see up here there's basically a crossover point where our distributed algorithms are winning even in high latency settings. So this is promising as we scale up to larger problems. All right, to conclude, we contributed a variety of things. First are two new incremental and distributed algorithms for maintaining STN temporal information. There's two variants. The first was DI triangle STP, which is fast and asynchronous. It propagates information very quickly throughout the network, but may suffer from redundant computation. And then the other has the opposite strengths. It is very meticulous in avoiding redundant computation, but does introduce some synchrony. By introducing these algorithms, we increase the independence with which agents can maintain temporal information. And our empirical comparison shows, general rule of thumb, if you're in low latency situations or understructured problems, you want to use DIPPC, whereas if you're in a high latency situation or if you have a highly structured problem, you want to use DI triangle STP. And we also contributed two corpora of MASTN problem instances. In the future, we hope to combine the constraints of these algorithms and get maybe a sweet spot in the middle. So two ideas for doing this is introduce more asynchronicity into the DIPPC algorithm, maybe releasing cliques to be worked on earlier. Or also you could think of making a priority queue for the DI triangle STP algorithm. So we don't just add queue in first come, first serve order. We prioritize triangles so that they're visited in perhaps a more logical order. All right, thank you.